everyone, and thank you for joining us today, grade 12. Today we're going to be looking at optimization problems or maximization problems, and specifically what we're going to be discussing and looking at when we're talking about optimization problems is we're going to be answering questions like, what is the most economical speed of a car? We're also going to look at what is the maximum area for a given set of constraints. And then we're going to look at something called rates of change, which is really what we've been doing all the time because calculus is all about rates of change. And here we'll talk about what is the velocity of an object at a certain point in time and what is the acceleration of an object as well. Okay, so just a reminder, and obviously this isn't an introductory lesson because we have started calculus a few weeks back where we went into detail as to what calculus is. And a reminder that calculus is all about rates of change. And today really we're looking at the applications of those rates of change. Okay, so we've looked previously at the rates of change of a slope, and we saw how the slope of a curve changed. And really when we think about calculus, we think about answering questions about the rates of change, obviously. But you may be able to answer questions like, what is the speed of a car? But when you're doing things like that, for example, I'm traveling at 60 kilometers per hour, that's an average. Okay, that's just an average over a certain period of time. But with calculus, and this is where the power of calculus comes in, is I can give you an instantaneous speed as well. So for example, I can tell you exactly what the speed of a car was at a specific point in time. So when the time was 2 minutes, when 2 minutes had passed. So you can actually give the exact speeds or the instantaneous speeds of the cars rather than just giving averages. And that's the power of calculus. We can take an average and rather than just look at an average, we can look at instantaneous quantities. All right. So the key concept we're looking at today, so if you have a look here, we look at something, for example, like the fuel used by a car, and I'm going to go through this whole thing with you. So the fuel used by a car is defined by an equation where you can see that the function value is a function of your speed, so f of v. All right, and you can see that v is the traveling speed in kilometers per hour, and we see that this is represented by a quadratic function as is given in your equation. The question then is, what is the most economical speed of the car? And if we have to think about this now and then interpret this a little bit differently, really what they're asking, in other words, is to determine the speed of the car which uses the least amount of fuel. So what is the speed of the car that will use the least amount of fuel? So if we take that function that you've been given, and we have to make a drawing of that, or we have to graph the function, you'll see my fuel consumption in liters per hour is on the y-axis, and then I've got my speed in kilometers per hour on the x-axis. And what you'll see is that your speed of on your x-axis is at 80 kilometers. When your speed is at 80 kilometers, then your fuel consumption is at a minimum. Do you see that? That's the minimum turning point of the graph. So when we think of it, the x-coordinate that gives us the minimum fuel consumption will be at the speed of 80 kilometers per hour. All right? So what you can see, as I just explained to you, and remember we can also use calculus. We have used calculus to find the turning point of a cubic function, but you can also use calculus to work out the turning point of any function. So here we've seen that the x-coordinates of the turning point can be calculated by differentiating the function, and you can find the x-coordinate speed in this case for which the derivative is equal to 0. Because remember, when your derivative is equal to 0, you're finding, if we're talking about graphs and we're interpreting it in terms of graphs, we're looking at where the stationary point is. So if we set the derivative of this graph is equal to 0, we can solve for the value of v that will give us the minimum fuel consumption. All right. Okay, so that's really what we're looking at there. And you can see definitely from your graph, and it has been also shown, and proven in tests and studies and that have been done, that there is an economical fuel consumption range for any car. So you might think, oh, well, the faster I'm going to save maybe 10 minutes in getting there. That's going to be worth way more than the cost of fuel I'm going to spend. It's actually not the case. Those few minutes that you save, you end up spending so much more money if you're traveling way too fast. You end up spending so much more money on fuel that it's not worth it getting there those few minutes earlier. All right, and also obviously if you're traveling at a more average speed, you're going to have less accidents. Okay. So so that's just what we can determine from this graph, and really this is the kind of thing we're going to be looking at, and this is how we can use calculus to answer questions like, what is the most economical speed of a car? All right. And we're going to then move on into our first question for today, where we're going to also now look at optimizing or minimizing a certain variable that we've been given. So here you'll see that you were given a container. It's made from cardboard, and you asked a few questions on this. I'm not going to waste time reading the whole thing for you. I'll do that after I've given you some time to look at it. So what I'd really like you to do here is to just have a look at this question, take down all the information you can, and list your important points that you can in your workbooks. And thereafter, we will do this question together. So this little time that I'm giving you is really just to read through the question, take down any important points that you need, and then we'll go over this together. So I'll give you 3 minutes to take this down. Okay, everyone, I hope that you had a chance to take down some of the key information. I know that it's not enough time to do the entire question, but we're going to go through it step by step now, just to give you a chance to get familiar with the question and understand what it is we're looking for. All right, so this is a typical type of question. I'm sure if you've done your optimization problems, you've seen these in textbooks as well. The first thing you want to do really, and remember today's the whole point of today's lesson really, and I know that when you look at these calculus word problems, they can become quite stressful and you don't know what to do. The main thing that we want to do in today's lesson is to maximize your success and minimize your stress. Okay, so if we do that, then we've succeeded. All right, so the first thing you want to do in this type of question is read through the question and take down any key information and note any constraints that there might be. So we are given that a rectangular juice container is made from cardboard. It has a square base and holds 750 cubic centimeters of juice. So what that means, cubic centimeters of juice, this is giving me the volume. All right, remember volume is measured in cubic centimeters. The container has a specially designed top that folds to close the container. The cardboard needed to fold the top of the container, and this is the important thing now. The cardboard on the top is twice the cardboard needed for the base, which only needs a single layer of cardboard. So if you think about what's that saying, so say you needed for your base, all right, say your base needed 10 centimeters squared of cardboard. Well, what they're saying to you is the top of this container is going to need twice as much. So the top will then need 20 centimeters squared, right? If the base needed 15 centimeters squared, then the top would need 30 centimeters squared. So all we're doing is we're timesing however much of cardboard we need for the base, we just times that by 2. All right, so if we were to extend this and we said that the area that we needed of cardboard for the base is x centimeters squared, then for the top of the container it would be twice as much, so it would be 2x squared. Okay, so that's really what that's saying to us, and that's going to help us to determine and to answer these questions. All right, to determine the value of x, I think it was, and h. Now you can see in your drawing that you are given that your dimensions of your base, your square base is x by x, it measures x by x centimeters, and that the height of the container is h. Now in these kind of questions you will generally be given some type of constraint or restriction, and we see that our volume of this container is 750 cubic centimeters. Now remember guys, that cannot change. That's what they've told you. That's a constraint. That's a restriction on this. This container can only take up to that amount of juice. That's it. Okay, so that's what we're going to use to help us formulate our equations and answer the questions that they've asked us, right? And what you also need to remember is the volume inside a container is unaffected by the amount of material on the outside of the container. So whether the top needs 2 times the area of the base and all of that, doesn't matter. It does not affect the volume. So that's a constant thing. Okay, it's not going to change. It's always going to be 750 cubic centimeters. So the first part says, if the length of the sides is x, show that the total area of the cardboard needed for one container is given by that expression there. All right, so let's have a look at it. We know so far, we know that the volume of this container is 750. Okay, so that's what we've been given. So I want to really already start making use of what I've been given. And if you can think of, if this is, remember, always study as if you're going to be writing a test or an exam on the question. And if you were thinking in terms of tests and exams, I want to get the most amount of marks as soon as possible. So if I've got my volume as 750 cubic centimeters, and that's a constraint, and that stays the same, I want to use that immediately, all right? So that I can get marks if this were a test. So we know that the volume, we determine that by saying area of the base times the height of the shape. Here we saw that the base was actually a square, right? So you know that the area of a square, side times side, is going to be x squared, and the height of the shape was given by h. So the volume is x squared times h. But we also know that the volume is 750 cubic centimeters. So I put that in. And the reason I want to start there, if you look at the question that you've been asked, or what you've been asked to show, you've been asked to show that the area is 3,000 divided by x plus 3x squared. What you'll notice there is that there's no h. Okay, so that already tells me I need to get rid of the h. And this formula for volume helps me to do that. Because if I've got x squared times h is equal to 750, the height in terms of x will be 750 divided by x squared. So I divide both sides by x squared, and I just get an expression for the height, which is going to help me when I'm working out the area of this shape. All right. So to work out the total amount of material needed, we really need to work out the total surface area of the shape. And what we know is that in this shape, we've got 4 sides, as you can see. So we've got 4 side shapes, all right, and there's the back and the front, and those are all the same measurement. So if I look at one rectangle, for example, on the side here, I can see that the area of that rectangle is going to be length times breadth, so it's going to be x times h, but there's 4 of those side pieces. So therefore the area will be the area of the sides plus the area of the base. And the reason we're separating this is because the base, the material used on the base and the material used on the top are different. So the area of the sides, we saw that it was x times h, and there was 4 sets of those. So therefore, it's going to be, all right, let's just get rid of that. It's going to be area of the sides, there's 4 of them, and we saw that it's length times breadth, which was x, h. The area of the base, it was a square, so therefore it's just going to be x squared. Now the area of the top, and we've discussed this at the beginning, we know that the top part of the container needs twice as much material as the base, so therefore the area of the top is going to be 2x squared. So it's twice as much as the base of this shape. Okay, so if I simplify this, we get 4xh plus 3x squared will be my total area of this shape. Okay, and now we've got to show, remember you've got to show, we're heading towards that. We need to show that the area is given by that expression. So what I'm going to do is, now that I've got my area in this form and I see that there's an h in this expression, I'm going to replace that h with the value for h that I determined using the fact that the volume was given to me. All right, so I'm going to substitute that. Okay, so we substitute that into the area equation. So I'm going to get that this is 4x times by 750 over x squared plus 3x squared. And if we simplify this, 4 times 750, you can double check that on your calculator, but 4 times 750 is 3,000 over x goes into itself once, and x divides into x squared, so that will give me just x in the denominator plus 3x squared. So that is my expression for the total area. Now for the next part of the question, where they said to you that you need to determine the dimensions of the container so that the area of cardboard used is minimized. Here we're going to work with what we already have. So we already have this expression for the total area, and that's what we now need to take and minimize. And remember, when you're minimizing something, in calculus, the easiest way, well, the only way really that you know how to do it, is to find the derivative. So that's what you're going to do. So what I want to do is, now that you've seen how we got this expression for the area, while we take a quick break, use that expression for the area to now determine the dimensions of this container that will minimize the amount of cardboard used. Okay, while you do that, we'll take a quick break. Welcome back, everyone. So I hope that you took that break to work out the solution to this, where we were looking for the dimensions of this cardboard box that will minimize the amount of cardboard needed. And you can imagine that these kinds of questions have a lot of real life applications, especially when you go into things like manufacturing and production, all right? Because manufacturers are always trying to minimize the cost of material used. Okay, so it all has a lot of practical application. Okay, so let's go straight into this. You've got your expression from the previous, just before the break. We saw that our area was given by that expression. Okay, and now we're going to look at part B. Just a reminder that part B said determine the dimensions. So we're looking here for the lengths, right, of the container, the length and the height of the container, so that the area of the cardboard used is minimized. So we want all the different sides. Okay. So in order to minimize a function, remember what you need to do is you first need to take the derivative. So the derivative of this area is going to give me the points. If you think of it in terms of graphs, right? Remember when we were talking about graphs at the beginning? When you're finding the derivative, in terms of a graph, you're looking for a local maximum or minimum value. You're looking for minimum points by setting the derivative equal to 0. You're looking for a stationary point. So this is exactly what we're doing here. It's a similar concept. Okay, so we want to find the derivative of that and where it's equal to 0, and that will help us to minimize the amount of material needed here by minimizing the area. So to find the derivative of my function, the first thing you need to do is you need to just simplify this so that it's in a form you can work with, guys. So don't write this straight into the derivative already. First simplify this. 3,000 over x is the same as 3,000 times x to the minus 1. Okay, how did I get that? Well, it's divided by x. So if I want to simplify this expression and work with it in an easier way, I need to change the position of the x, so I take it to the numerator. How do I do that? I change the sign from a positive 1 to a negative 1. Okay, so now that my expression is in that form, it's perhaps a little bit easier to derive. So to take the derivative of this, I'm going to get minus 3,000 x to the minus 2, so I times through. What am I doing there? I'm just deriving. I'm taking the power from the negative 1, multiplying it by the coefficient of 3,000, so it becomes negative 3,000, and from the minus 1, I subtract 1. That's just your rules for differentiation, okay? And then we derive the second part of this expression, so I get plus 6x. We want to minimize this, so this is where your function of your area is equal to 0, so you set that equal to 0, and this is where we're going to solve this expression. Okay, so let's write this in a way that it's a little bit easier to work with. So it's minus 3,000 over x squared. What am I doing there? I want to work with the positive exponent for x, so I've changed its position. I've moved it from the numerator to the denominator. So it's minus 3,000 over x squared plus 6x is equal to 0. Now we are dealing with an equation, so in order to simplify this or to get an answer to this, what we need to do is to find an LCD, a lowest common denominator. I see my denominator is x squared, so I'm going to times through by x squared, and I get minus 3,000 plus 6x cubed all over x squared is equal to 0. And provided that x is not equal to 0, we can leave the x out. We times through by the x squared, so we get minus 3,000 plus 6x cubed is equal to 0. So 6x cubed is equal to 3,000. And then we divide both sides by 6. So we'll get x cubed is equal to 3,000 divided by 6 is 500, and then we're going to take the cube root on both sides to just get x by itself. So I'll get x is equal to the cube root of 500, and that you're going to need your calculator for, and we'll get a decimal value here. So it's going to be shifts cube root 500, and that gives us 7.93. Okay, so I'm going to round that off to 7.9 centimeters. Okay, so that's going to be 7.9 centimeters. But remember, you're not done, because that's just the length of the side of the square base and the length of the sides. We need to find the height. Remember, the height, we saw that we had an expression using the volume was 750 over x squared. So therefore my height will be 750 over, and you're going to use the answer that you had in your calculator there, over 7.9 squared, and that's going to give you an answer of approximately 12 centimeters. All right, so that's approximately 12 centimeters, and that will be the height of this shape. Okay, so really what you've done is you've found the dimensions that are going to help you make a box that will have the minimum use of cardboard. Okay, so far what we've discussed are optimization problems. We also mentioned that we're going to be discussing rates of change, and that's the next thing that we're going to be looking at here, where we're looking at acceleration and we're looking at velocity and speed and all of those things. All right, so have a look at this, and here we're discussing, as I said, rates of change. We're looking at how fast things are changing. So mathematically, we know that we can represent change in different ways. We've seen that we can use algebraic formulae, and we can even use graphs. Now, graphs, remember, those are your visual representation of the rates at which a function value changes as your independent or your input value, which is normally given by x, as that variable changes. This rate of change is described by the gradient of the graph, and therefore can be determined by calculating the derivative. Now you can think about why that works. Remember, when we try to find the gradient of the graph, we know that that's equal to the derivative of the graph as well. All right, so that's what we're basically saying there. We have learned how to determine the average gradient of a curve, and remember, your average gradient is really you're looking at the change between 2 points, all right? And how to determine, we've also learned how to determine the gradient of a curve at a given point in time. So that's your instantaneous rate that we were talking about. These concepts are referred to as your average rate of change when we're looking at the average gradient, and the instantaneous rate of change when we're looking at the gradient at a given point. So just a reminder of what all these words mean, because in maths we don't like using so many words. We like looking at formulae, and it makes things a little bit easier to work with. When we were looking at average gradient, we were looking at the change between two function values, and we divided that by the difference between the two coordinates, the two values, your input values, all right? So for finding average gradient, we looked at f of x plus h minus f of x all over x plus h minus x. So if we're looking at it in terms of graphs, we're looking at the average gradient between 2 points x and x plus h. Okay, and then what we introduced was this concept of a limit, and this we did right at the beginning. And the concept of the limit enabled us to find the instantaneous rate of change. So when we add into that same formula for average gradient, we add in the limit as h tends to 0. All right, what we saw there was that this point, we're really saying this distance is becoming smaller and smaller and smaller and smaller until we're finding the gradient at a specific point in time, and that gave us the instantaneous rate of change. All right. So when we mention rate of change, guys, and this is important, automatically, when we're talking about rate of change, we're talking about the instantaneous rate of change. So what's happening at one point in time. If we wanted you to find average rate of change, and this is in an exam or a test situation, or even when you're doing your homework examples, if you were looking for the average rate of change, the question will say, all right, so the question will specifically say, look or find the average rate of change. Now, one of the most common rates of change that we look at is velocity. And velocity, obviously, if you do physics, you've heard this in physics as well. So velocity refers to the change in distance for a corresponding change in time. So if we look at any function, like your function v of t, that will be the change in distance with respect to time. All right, so that's the derivative. We can say s prime of t, so we're deriving the distance of a function or distance function to give us the velocity function. Okay. Now, acceleration is the change in velocity or speed for a corresponding change in time. So therefore, your acceleration is the derivative of velocity. Now, think about that. So to find acceleration, I need to derive velocity. But in order to find velocity, I needed to derive distance. So therefore, really what we're saying is that acceleration is the second derivative of distance. Okay, so these concepts, this is all really just a theory. We're building up to something, obviously. So we're building up to a point where we need to use this in applications of finding velocity, acceleration, when we are given the distance and the time. Okay, so that's the kind of thing we really want to discuss. And I think what we're going to do, because it is quite a long discussion, and I've got a question for you to do on this concept of what is acceleration, what is velocity, how does it relate to an object's movement. I really want to discuss that in full without any break. So we're going to take a quick break now, and then when we come back, we'll go straight into our question relating to velocity, acceleration, and speed, distance, time. All right, after this. Welcome back, everyone. I hope that you're now understanding your optimization problems a lot better, and you're understanding rates of change as well. So we went through a bit of an explanation of rates of change before the break, and now it's time for us to use and apply the knowledge that we have learned so far in an actual rates of change question. Okay, so I'm going to give you another typical example. So if you have a look at your screen there, you're given that a soccer ball is kicked vertically into the air, and you've got its motion represented by an equation, and in this case we've got a quadratic equation, and you've got a couple of questions. So what I'd like to do, guys, is I'm going to give you a few minutes just to take down this question, get yourself familiar with the question, and there's 4 parts. Well, yeah, 4 parts in the first section here for number 2, and then later on there's another 5 parts. So let's just start with this bit here. Take down questions A, B, C, D. Make sure you've got all the information and that you know what's the key bits of information that you need as we go through this question. So I'll give you 2 minutes to take this down. All right, everyone, so you had enough time now just to take the question down and to understand what's happening. So here you've got someone kicking a soccer ball into the air. You can imagine the motion, right? And we've got an equation that represents this motion. And now you've asked been asked various questions about the velocity and the height of the ball. Let's go through the question together. Okay, you see that the soccer ball is kicked vertically into the air and its motion is represented by that equation. You are told that d is the distance above the ground in meters and t is the time elapsed in seconds. All right, so before I have a look at the question, let's just kind of sketch what could be happening, what kind of motion are we seeing. So we see the ball is kicked into the air and then obviously it's going to start falling back down to the ground again. And you have, you've got an equation that describes this motion as well. All right. Just need a bit more of page up here. All right, so this is what we're looking at, and we've got a ball that's being kicked from that point there. It's going to go up. At some point, it's going to reach a maximum, which we know is going to definitely happen, and then it's going to come back down again. Okay, so just from the laws of physics and what's going to happen to this ball, it's got to go up, reach a certain point, and then come back down to the ground. Okay, it's not going to stay up there forever. It's got to come back down. Okay, so we are asked to determine the initial height of the ball at the moment it is being kicked. Now, if you think about this, the moment this ball is being kicked up into the air, no time has actually passed. Okay, so we're looking for the initial height of the ball from the moment it's being kicked. So that means that your time there is 0. So for A, we know the time is equal to 0. We are asked for the height of the ball, and we know that the equation that gives us height is this one. All right, that's the equation that gives us the distance above the ground in meters. So therefore, if I want to know what the height of the ball is when time is 0, I replace t in that equation with 0. So it's going to look like this: 1 plus 18 times 0 minus 3 times 0 squared. All right, so if you have a look at that, you'll get an answer of 1 meter, because obviously those two values will cancel out to just give you 0. So therefore, the initial height of the ball, it's already 1 meter in the air when you kick the ball. Okay. Now, guys, we're going to look at part B. Now, remember here we're going to be looking at velocity. Now, when you think about velocity, and we spoke about this before the break, velocity is going to be the derivative of distance. Okay, so therefore we're going to need to find the derivative of our distance equation in order to answer part B, which is find the initial velocity of the ball. So once again, because we're looking at initial velocity, our time is equal to 0, but here we're dealing with a derivative equation because we're looking for the velocity. So the derivative of our distance equation is going to be equal to 18 minus 6t, and then we want to substitute t is equal to 0, which will give me the velocity at time 0, and that's going to give me 18 meters per second. So you kick this ball up with a velocity of 18 meters per second. Now, for part C, let's have a look at part C. It says determine the velocity after some time has passed, so after 1.5 seconds. So here, once again, because we're dealing with velocity, we're going to deal with the derivative equation. So we've got time is equal to 1.5 seconds. And we're using the equation of the derivative. I'm simply going to replace my t with the value of 1.5. So my equation becomes 18 minus 6 times 1.5. And when you do that on your calculator, you will get an answer of 9 meters per second, and you can just double check that, but for time we're not going to check that on the calculator. And then part D says calculate the maximum height of the ball. So obviously we know this ball's going into the air, it's going to reach some maximum point, and then it's going to start dropping once again back to the ground. So to find the maximum height of the ball, when you're thinking about calculus and you're thinking about maximums or minimums, that tells me that I need to derive. All right, so I already have my equation of the derivative. We know that the derivative is equal to 18 minus 6t. Okay, so to calculate the maximum height of the ball, that's where my derivative is going to be equal to 0. So therefore, I'm going to have 18 is equal to 6t. I take the 6t over to the right-hand side, and I solve for t, and I get 3 seconds. So that tells me that it's going to take this ball 3 seconds for it to reach its maximum height. All right, so the ball takes 3 seconds to reach its maximum height. In order for me to determine the maximum height, I now need to go back into my original equation, which gave me an expression for the height, which was 1 plus 18t minus 3t squared, and that's where I'm going to substitute my t is equal to 3 seconds back into the equation that gives me the height. So I get 1 plus 18 times 3 minus 3 times 3 squared. You can double check that on your calculator, but you're going to get an answer of 28 meters. So therefore, the maximum height that this ball reaches in the air is going to be 28 meters. Now, guys, I just want you to do a few more questions. We'll really just take down a few more of these questions, which we'll go through together. But I'm just going to give you a few minutes, just 2 minutes, to once again take down, dealing with the same problem where we've got this ball that's kicked into the air, the same question, but now we're going to look at a few more points, and we're going to extend velocity and look at the acceleration. All right, so I'm going to give you 2 minutes to take this down. All right, everyone, so we don't have much time to go through each and every one of these questions from E to I. What I'm going to do is I'm going to do E and F with you, or try to get through E and F, and I'm going to give you the answers to G, H, and I, and you can do this as homework and then double check your answers. All right, so firstly, I just want to give you the answers to G, H, and I. So if you have a look at your screen, when you do this for homework, for part G, determine the velocity after 3 seconds. You should get an answer of 0 meters per second, and you can double check this once you've taken this down and done this for homework. And then part H, how long will it take to hit the ground? You're going to get T is equal to 6,05 seconds. And a hint here, you're going to need to use the quadratic formula. Determine the velocity of the ball when it hits the ground. Here you're going to get your velocity is minus 18 meters per second. All right, but let's quickly go through E. Determine the acceleration of the ball after 1 second. Now, I've said to you right at the beginning when we started talking about rates of change is that acceleration is the derivative of velocity, or in fact, acceleration is the second derivative of distance. So therefore, for part E, where I want the acceleration of the ball, I am going to take the second derivative of my distance. Okay, or it's the same as taking your derivative of your velocity function. All right, so remember your first derivative was equal to 18 minus 6t. So therefore, for the second derivative, I derive that expression and I'm going to get an answer of minus 6. All right, so I've got 18 minus 6t, derive that, I get minus 6. So therefore, when it says to me, well, what is the acceleration after 1 second? You can see that I've got nowhere to actually place this 1 second. It seems like my acceleration is going to be minus 6 meters per second squared anyway, all right, always. So the acceleration of the ball is after 1 second is minus 6 meters per second squared. Explain the meaning of your answer. Well, what's happening? Why is it negative? What's going on there? Well, the velocity, this must mean that the velocity is decreasing. The velocity is decreasing by 6 meters per second. All right, so the velocity is decreasing by that amount. And then for part F, it says calculate the average velocity. So here it's not instantaneous, average velocity of the ball during the third second. This is where you're going to find your change in distance from second 2 to 3 over your change in time. So that's a D, change in distance over change in time. If you do that, and we're going to write this down very, very quickly. So this is part F. You're going to say D of 3 minus D of 2. So your distance at 3 seconds minus your distance at 2 seconds, all over the difference in time. And when you work that out, you'll get an answer of 3 meters per second. And that is your average velocity during the third second. So very quickly, guys, just to recap, we've seen how we've used calculus to work out the turning points and slopes of curves. And in this lesson, we looked at speed and maximization problems. And remember that calculus is all about rates of change. If you want to maximize or minimize an amount, you need to find the derivative. And that will give you your optimum point, okay? You then, if you want to see if that point is your maximum or minimum value, you take your second derivative. If the second derivative is positive, you find a minimum value. If the second derivative is negative, you found a maximum value. Okay, and hopefully today we have maximized your success and minimized your stress in these types of problems. Until next time, cheers.